So, good morning, ladies and gentlemen. It's a pleasure to be here. My name is Dimri, and I'm going to be talking about the effects of nuclear shape fluctuations in the initial state observables of heavy ion collisions under the Glauber framework. So here's a basic outline of my presentation. I'll try to quickly introduce the topic, and we'll see a bit about the liquid drop model estimates. And I'll briefly explain what is the Glauber model. Then finally, we'll discuss our results, and then I'll briefly summarize everything that I've talked about. So in this slide, I present to you the various stages of relativistic heavy ion collisions. But for the purposes of this slide, consider this entire evolution as a huge black box of which we know everything about. So this entire schematic reduces down to a very simple algorithm, which is simply that we have some initial stage inputs, which goes into this black box, and then it gives us the final stage outputs in the form of particle spectra. Now, it's quite logical to say that if we don't understand our initial stage inputs, our understanding of final stage outputs will not be complete. So it's kind of important to understand all these initial stage inputs. In our case, these initial stage inputs are basically the energy deposition mechanism into the overlapping area. And the second thing is the nuclear structure of these colliding nuclei themselves. Now, in this talk, I'll basically be talking about the effects of nuclear geometry onto the final state observables. And this nuclear geometry is generally parameterized by this famous deformed Wood-Saxton distribution. The function r of theta and phi is what controls the shape of the nuclei. If this function were a constant, then the shape of the nuclei would have been a spherical shape. And we introduced quadrupole deformations by this term over here, which is parameterized by two deformation parameters. One is the parameter beta and the other is the parameter gamma. The parameter beta basically controls the magnitude of an axially symmetric deformation, while the parameter gamma controls the relative ordering between the three axes of the spheroid. This can be seen in this top line of this bottom graph, where a value of gamma equal to 0 gives you a prolate nucleus, gamma of 30 gives you a triaxial nucleus, while a gamma of 60 gives you an oblate nucleus. Now you guys can ask that why are we putting in quadrupole deformations? Well, there are two basic reasons for that. The first one is that quadrupole deformations are the simplest form of deformations that can be inputted into the intrinsic frame of the nucleus. And second, theoretical calculations show that almost all of the nuclei, which are not magic nuclei, have some form of quadrupole deformations. This can be seen in this curve on the top over here. The lines here denote the magic nuclei, which are basically more or less spherical, but other than that, you can see that most of the nuclei has some form of quadrupole deformation in it. Now, if you see this, now I would like to bring the attention towards this lower curve of the bottom figure, and you see, depending on the shape of the nucleus and the orientation between the projectile and the target, you can get a variety of different overlapping regions. These overlapping regions are like the inputs that we are going to give into the black box. So of course, if we change any of the inputs, the final state outputs will change. And so it's quite logical to expect that these change in nuclear shape will affect the observables in the final state. If life would have been simple, the shape parameters would have been fixed. They would not fluctuate. But as it turns out that it is not quite so easy. So if we try to draw the potential energy surface as a function of the deformation parameter beta, we can get a variety of curves. For example, for the vibrator and the rotor case, what we'll have is a sharp minima. And so small amount of fluctuations are really not going to affect our system. However, if we have a soft system in which the potential energy curve is flat around the minima, what can happen is small amount of excitation energy, which can be produced even by the collective modes of the nucleons within the system. What they can do is change the value of this parameter beta. As we saw earlier, deformation parameters basically control the shape of the nuclei. So a change in the value of this parameter can be indirectly looked as a change in the overall shape of the nuclei. Now, this exercise can also be done for not only in one dimension, but in two dimensions with two separate deformation parameters. On the lower left graph, what is shown is the equipotential surfaces for the quadrupole deformation parameters beta and gamma, and similar analysis similar kind of inferences can be drawn. For this particular curve, if you look around from 0.2 to 0.3, and if you look in the direction of gamma, which is this circle over here, you will find that it is actually quite soft. That means that the minima is very, very flat around this point. Not only you can do all of this stuff with the deformation parameters of a single type of deformation, you can do it with even different type of deformations. What do I mean by that is you can draw the equipotential surfaces as a function of beta3, which is basically a deformation parameter for octupole deformations, versus beta2, which is the deformation parameter for quadrupole deformations. And again, if you would have seen that in this curve, you find a flat minima, and then it would mean that small excitation simultaneously changes the values of beta3 and beta2, which would translate to have that the nuclei is able to change both its quadrupole and octupole deformations at the same time. So the possibilities are basically endless on how this can happen, and all of this depends on the profile of this potential energy surface. For this presentation, I'm simply going to talk about only quadrupole deformations, which are parameterized by the parameters beta and gamma. So in these two lower left plots, what they have shown is that for a static deformation. So right now in these plots, they have inputted some fixed value of beta, some fixed value of gamma, and they allow no fluctuation. And what they see is that the effect of these deformation parameters is quite pronounced in the ultracentral collisions. As this, the left plot is shown for second order of eccentricity, and the right plot is shown, and this shows the effect of beta parameter. And this right plot, it is shown for the ρ2 ratio, and it is shown for the gamma parameter. As you can see, you can clearly, very easily distinguish what kind of gamma parameter you have by looking at the central collisions. So now that we know that fluctuations are a real possibility, it's quite natural to ask, okay, what would happen if I have a gamma mean value of this, but it fluctuates largely around this? So will my value decrease, increase, go towards this? It's kind of interesting to ask what would happen. So before we look at the Glauber simulations, let us see what we can expect from it. And to do that, we just look at the liquid drop model. The liquid drop model simply implies that my nuclear matter has a uniform density inside it, and it has a very sharp surface. The third thing that I have assumed in this for this calculation is that the impact parameter is 0, because as we saw earlier, the effect of deformation parameters was most pronounced in the ultracentral collisions. So if you perform a first order analysis, these are the two variables which are of our interest. The first are the relative fluctuations in inverse transverse size. And the reason that this initial state parameter is useful is because it is proportional to fluctuations in transverse momentum in the final state. The second observable that we will have is the eccentricity, and it is useful as it is proportional to the elliptic flow in the final state. So you kind of have, so if you just look at these two variables, you can kind of get an idea what happens to these initial state variables. Now, these are actually event quantities which are not very useful to us. So we kind of need to take an event average over all of these quantities. And when we do that, what happens is we kind of get two separate averages. One is the average over all the orientations between the two nuclei, and the second is the average over all the fluctuations of these deformation parameters. So once you are armed with all of this information, you can calculate any cumulant and you can get its leading order approximation. Now, for our analysis, these are the 5 cumulants that we actually calculated. They are basically variance and skewness in relative fluctuations of inverse transverse size, the second order of eccentricity, the fourth order cumulant of eccentricity, which is sometimes also called C2 epsilon, and this mixed cumulant, which is sometimes also called the covariance. What you need to take away from this slide is that if I have an n particle correlation, which is basically the total power of the observable on the left, the leading order moment that would come out would be beta to the power n. I'm sorry, that was kind of confusing. So in very simple terms, if you have a 2 over here, total power is 2 over here, the leading order term would be proportional to the second order moment of beta. If it is 3, it will be proportional to third cubic moment of beta. And if it's 4, it will be proportional to the fourth order. Another thing that I would like you to take away from this slide is that for this particular cumulant of eccentricity, the ratio between the quadratic square term and the complete pi quadratic term is 7 over 5, which is roughly 1.4. And this will be useful a bit later in the slides. Now, let's quickly understand what is the Glauber framework. So what the Glauber model does is it produces a Cartesian system in the XYZ plane. It initializes the two nuclei and then it fills it with nucleons using this deformed Wood suction distribution. Finally, it samples an impact parameter from B bin to Bmax. And for our case, since we wanted to fix it to 0, we just set both in values equal to 0. Then the nuclei are sent towards each other, participating nuclei are identified, and even quantities are computed.
Now, this calculation is done in the p equal to 0 case.
Yes, this calculation has been done for p equal to 0. So that has been fixed by me by hand. So finally, let's go towards the results. First, I'll talk about gamma fluctuations, and I'll basically focus on three particle correlations, the covariance and the skewness in inverse transfer size, which is sometimes also called TD3. Then after, I'll go to the effects of beta fluctuations, and I'll discuss the two particle and the four particle correlations. The two particle correlations are second order of eccentricity and this variable called CD2, which is variance in the inverse transfer size. And this is simply the fourth order cumulant of eccentricity. So the first thing that we need to do to find the impact of these gamma fluctuation is to be able to parameterize into some form of fitting equation. So now no matter what happens, we know that any observable which has to depend on gamma has to have a period of 2 pi, because gamma, you can take gamma plus 2 pi. It is the same angle in terms of the deformation parameter. Now, if you have a periodic function, then you can definitely write it in terms of a Fourier series, and that's what we have written. In addition to that, we know that nuclear shape has a threefold symmetry under this triaxial parameter, and that is why the terms inside the cosine comes as a factor of 3 and gamma. So it can only be a multiple of 3, some multiple of 3. If we look at this formula carefully, what you will see is that I have already incorporated the effect of deformations in this formula. For the time being, I have assumed that the fluctuations, the deformation parameters are of Gaussian nature. So for purposes of gamma fluctuations, it is being sampled from a Gaussian distribution, which has a mean gamma bar and a variance sigma gamma square. And so the effect of mean is to simply replace its value over here. And while the effect of variance is to exponentially decay its corresponding value with a prefactor of n square over 2. Now, after this, what we saw in our data is that for this particular line, which is the triaxial line, we saw that it doesn't really depend on the variance parameter. It is constant throughout the entire set of simulation that we use. And this is true for all of the observables that we saw. I show you this explicitly for the three particle correlations on this slide. Okay. And on this slide, I show you that this is not only true, it is also true for even all the other three observables, for which the triaxial signal was roughly 10% of the base signal. So this is kind of very robust. So we
the sigma gamma at the bottom.
So I'm sampling gamma from a parent distribution, from a parent Gaussian distribution to introduce fluctuations into its value. So this is the variance of that.
Variance to the standard deviation.
Sorry?
The variance of the standard deviation.
So sigma would be the standard deviation, sigma square would be the variance. Yes. Okay. So the thing to note is no matter what kind of observable you look at, you will see that the triaxial parameter doesn't really change its value when it doesn't really change its value as a function of this standard deviation of variance parameter. So we kind of need to input that into a function. This is an additional constraint of which we don't really completely understand. And this can be simply done by subtracting the values of the triaxial parameter. And so our observable in the most general case looks something like this. Now, if we restrict ourselves to leading and subleading terms, we will get these three basic terms. The A0 term, which is the residual effect from any beta term that we might have left. The first order terms, which are proportional to cosine 3 gamma and cosine 3 gamma, and with an exponential decay term proportional to sigma gamma squared with a prefactor of 4.5. The subleading terms are similar, but this time the factors are 6 gamma and the decay factor is 18, which is roughly 4 times what we had for the leading term. So we can already expect that subleading terms are going to not contribute too much. So let's now have the impact of these gamma fluctuations on our three particle correlations. Now there are three main things that needs to be noted in these plots. So if I draw your attention to this left-hand curve, which is of covariance, you will see that when sigma gamma is 0, which means my deformation parameters are static, I have a clear large triaxial signal. As I start inputting fluctuations and the variance of my distribution increases, the triaxial signal starts to decrease. At roughly 20 degrees, when the fluctuation is roughly about 20 degrees, the signal has already reduced by 1/2. So it's a 50% reduction. And if I keep on increasing, I see that all of these curves basically merge into one another. So what that means, like if I have large amount of fluctuations, or in other words, if I have a nucleus which is fluctuating uniformly between prolate and oblate shapes, then it is not possible for us to distinguish it from a rigid triaxial nuclei, which is this particular line. You can see similar inferences for our second variable CD3. However, this time around we have a small asymmetry about this triaxial line for the prolate and the oblate nuclei, and so that is taken care of by our subleading terms in the expansion. This particular behavior of having some triaxial signal rapidly decreasing and finally merging is very, very robust, and is not only seen in these three particle correlations, which has a major triaxial signal, but also for all the other three variables for which the triaxial signal is just 10% of the baseline. So this triaxial signal is just 10% of this triaxial baseline, but all of these very robustly follow the same exact pattern as we saw before. And so all of the same inferences also apply over here.
So 2 minutes before discussion.
So finally, let's talk about the impact of beta fluctuations. Now, if you remember that in the liquid drop model, we only expanded up to beta in the event level. What we can do in the most general case is expand it as a power series. Of course, we can truncate it somewhere. And then if we take an event average over all the observables, what we will find is that we get two kinds of terms. One is this term is coming direct, is a direct term which is coming directly from this particle or target. And then we have a mixed term which is coming because of a cross between this projectile and target nuclei. For this particular analysis, what we will see is that for us, it's more or less quite enough to expand eccentricity up to second order at the event level to explain all of our graphs. So let's have a look at the impact on second order of eccentricity and the variable CD2. First of all, we notice that the curves are almost linear, so they can mostly be described by some linear function. We also notice is that the slope for these different curves, which represent different values of sigma beta, so as I vary my sigma beta, the slope varies a little bit. So I kind of can say that the slope has some dependence on this parameter sigma beta. So now that we have these two observations in mind, to describe both of these features, what we do is expand this into the first three useful moments, which would be 2, 3, and 4. Because these are two particle correlation, that's why it starts with the second order moment, because this has to be the leading order. And so what we see is that the second order of eccentricity, it is almost linear, has a major contribution from beta square, has a negligible contribution from the cubic term, and has a very small correction from the fourth order term. And for this particular variable CD2, all of the three moments are required to explain this Glover data. Now, finally, let's have a look on how it impacts this particular variable C2 epsilon. And if we remember from previous slide, what we saw is that the cubic order moments was not really useful. And so I wanted to minimize the amount of parameters used for the fit. So I expanded it into the first two non-zero moments, which would contribute to this particular variable observable. And for this, it turns out it's the biquadratic and power 6 term. Naively, the positive terms are directly coming from this epsilon 2 to the power 4 average, and the second negative terms are basically coming from epsilon 2 squared when it's completely squared. what we see is that this particular function describes the global data quite well. And another thing we see is that when I have static deformation, the value of this particular observable is always negative, and it increases with the increase in mean value of the parameter beta. This can be seen directly in this top curve over here, and this is visible on the lower curve in the form of these red points over here. What is interesting to notice is that as soon as I input a small amount of fluctuations, the value of this particular observable turns quickly positive. So this can be seen in this green curve, in which the value of the variance is just 0.02, while the value of the beta squared over here is roughly 0.1, which is 5 times the variance. And even though it's 5 times, the value of this particular observable is still positive. So if you do a calculation in data, and if you see that you have a large negative value of this particular variable, it can be an indication of static quadrupole deformation present in the system. Not only that, if you look at the parameters B1 and A1, what you would find that the ratio between the parameters B1 over A1 is roughly 1.5. And this is very, very close to the ratio that we saw for the liquid drop model, which was 1.4. Now the liquid drop model assumes uniform density, while Glauber model is a completely different model, which actually inputs nucleons over there. And so if we are a bit brave, we might be able to say that this particular ratio is independent of system size for this particular variable in the ultracentral collisions. So finally, I try to summarize what I talked about in this presentation. The first thing we saw is that fluctuations in the deformation parameters do have some effect in the final state observables, in the initial state observables under the framework of Glauber model. We saw that when we input fluctuations in the triaxiality parameter, the triaxial signal decreases very quickly, and as the variance becomes very large, it becomes, or the observables fail to distinguish between the prolate and the oblate deformation. For quadrupole deformation, we saw that they can be explained using the moments of in terms of the moments of the parent distribution. And we saw that if C2 epsilon is basically negative, then it might be an indication of having some static deformation within the nucleus. Thank you all for your attention.
Yeah, so for the C24, just to remind me, so you're talking about where if I want to get to B2, I'll take a negative sign and.
Yes, yeah.
Okay,
Yes.
so that means that if you have a real one, then you'd expect the static.
Yes.
Okay, so are there, I think for uranium, that was the case, if I remember correctly, in ultracentral, but every other nucleus is always imaginary, if I remember, that's correct, okay. Thanks.